Okay, welcome to this screencast for 5.5 is actually in our Unit 6. It's multiple angle and product to sum formulas. So part 2, product to sum formulas and sum to product formulas are what are going to be the focus here. So what you see, just as the name would suggest, on the left-hand side of each of these formulas, you have a product. You have the sine ratio of some angle u times the sine ratio of some angle v. It's a product, and you are able to split it up, so to speak, into a sum. In some cases, we would almost maybe call these or difference formulas. Okay, because in this case, notice if I had that product on the left, it is now the subtraction on the inside of the cosine ratios of either the difference or the sum of that cosine, and then you divide that thing by 2. I guess begs the question, why would I need this in this direction? I guess if you had that product, you wanted to turn it into a sum. Couldn't think of it. Maybe for evaluation purposes? Well, we'll see how these examples unfold. Going the other way, I think it's for solving purposes definitely easier, and then maybe these first ones for evaluation purposes, or maybe if you knew a given value, that's why you'd want them. Anyway, the purpose of this is to show you some examples and then work through those, and we'll be all set. Okay, the first one that we'll go through, this first type, is to rewrite a given product, cos 5x sine 4x, as either a sum or a difference. Okay, and then go ahead and simplify as well. So you would be given these formulas, and you would scroll through them, and you would notice, okay, I've got the cosine of something and the sine of something else. And so scroll through your formulas, and you'll notice if I have a cosine of a certain argument, is actually that's called, something being sined or cosigned. If I zoom in a little bit, you have that right over here. So the cos of something times the sine of something different can be simplified actually using that formula. Okay, in this case, I guess we'll see where this leads to. We won't have the ability to evaluate, but we'll see where this leads to. Okay, so see if you can understand how to do the substitution and then simplify as far as you can, and I'll come back with the solution to see maybe how you did. Okay, so if we move just little by little here, first step is to identify, well, there's a something, that's the 5x, and so I'll call that my u, and then something different is my 4x, so that'll be the v, and then I just went ahead and just plugged it in the way we see it there. Okay, and then we can certainly bring together those pieces on the inside, right? So you have the half of the sine of 9x minus sine x. I guess at the very least, you now have the same ratio to take, the sine ratios, and so it feels a little bit simplified. You could take that one step further and distribute the half. Okay, so two different ways, I guess, that we would say that's fully simplified. You would either go like this, I guess, or you would take it that way. Okay, I happen to think probably the simplest of them all is that bottom right-hand corner. Okay, there you go. That's one example. So just spotting how to use a formula when you're given something. The second type is to go from a sum or a difference. Okay, so technically a difference really is a sum because it's just adding a negative. So I'm just updating this. I guess you're given a difference or a sum. So like this is a sum and this is a difference, and this is a sum and this is a difference. And some of you might be wondering, well, why can't I thought we had sum and difference formulas already. Well, yeah, just going back here live on the screencast. Actually, I'm in the wrong screencast, sorry about that. Those sum and difference formulas, not to be confused with those ones, those were when the angles are actually being added or subtracted, right? You had a different scenario altogether. So these are, you have a sum of two separate ratios happening, right? Not like the case of the sum difference formulas, which I'll just get up on screen. Yeah, sorry for the fumblery there. I just had to get a different Jamboard up. Those were the actual sum difference formulas where you actually had a sum or a difference in the argument of the angle, and then you could spread it out in the ways that we saw, okay, for different purposes. This is, you have two separate sines or cosines that are being summed or differenced, and then this is the way that you would simplify it. Okay, now why would we do that? Okay, well let's check out an example, and we'll see why. There's two different types of examples. One is an evaluate and one is a solve. Okay, so I'll cue those up and we'll be ready to go. Okay, this first type, example 8, is an evaluate style one. So asking you to find the exact value of cos 195 degrees plus cos 105 degrees. So this is a situation in which, using those ones that I just showed, the sum difference, you could break 195 apart into a couple of pieces, right? And then try to use your sum difference that way. But this, by virtue of the fact that it actually is the summation of a couple of different coses, instead of having to break apart and do a lot more work, the mathematicians did a little bit more digging, and they were able to figure out this formula. So you're still actually doing kind of the same concept. If I zoom in on that formula, we are going to have to come up with some addition in here. So our u plus v, though, and our u minus v, as opposed to breaking up 195 into some convenient combinations, we're actually going to take the u's and the v's and add them together. Okay, so see if you can add that together and see how far you can get. I'll take it little by little again when we come back. Again, no calculator involved here, so you'd have to break it apart. You'd have little blue, I guess, to do 195 plus 105 if you needed to do that. Okay, I'll advance things a little bit here and talk about it in a sec. Okay, so plain and simply, that is the substitution. Would have thought everybody could get that far, where the u is 195 and the v is 105. Get my little sticky note out of the way. That's what I was talking about before. Technically, we could have used those other sum differences. And then thinking that everybody could have got one more step there to get to 2 times the cos of 150 and the cos of 45. So this is really cutting down on the work, I think. If you had tried to break it apart before, that would have been harder. So now you're at cos 150 and cos 45. We should be able to come up with those values. I've made a diagram for what you would have to be thinking about for cos 150. Notice that it's in the second quadrant, so that's going to be a negative value. Cos 45 is definitely a positive value from your chart or your unit circle. See if you can take that all the way to the end and then come back to see if you were right. Okay, so should get down to negative root 6 over 2, fully simplified. 2 is 2 over 1, and negative root 3 over 2 is the cosine of 150. Root 2 over 2 is the cosine of 45 degrees. And so then you've got 2 over 4 times root 6. 2 over 4 simplifies to a half, so you've got negative root 6 over 2. Okay, that is example 8, all wrapped up, and then we're on to our last example. Okay, so example 9, that's a big one. It looks innocent enough. Just solve sine 5x plus sine 3x. Again, you're given a list of formulas, and it would be up to you to try to think about a way that you could get to solving that. Little sticky note there, why would we take that sum and turn it into a product? And the answer is to use the zero product property. Okay, trying to split this 5x or this 3x up into different stuff using sum and difference, that can lead you, that would be a lot of algebra. Whereas this one, zooming over to the right side, if you can let 5x be your u and 3x be your v, see where that can lead you. Might not have a clear path to the solution maybe in mind just yet, but go ahead and try that, and that's what I'll do first. And see why a product is better here than the alternative. Okay, so if we're working with this in our sum to product with our u and our v as 5x and 3x, then we can substitute into our formula and simplify, right? 5x and 3x is 8x, over 2 makes 4x, and then 5x minus 3x makes 2x, over 2 makes just the single x there. Actually, sorry about that. And what's the advantage of having transformed this into a product is you can see me just up in the top there adjusting that into a situation where we have the zero product property that we can use. So you've got the number 2 times sine 4x times cosine x equals 0. What would you do with that? I'm going to pause there, see if you can make some progress on your own. Okay, hopefully, and I just paused here, hopefully that you're noticing that's the value in getting this to a product, right? We're going to use our zero product property. We want to get to these trig equations just in one function, and we can go from there. The equation on the left, a little bit more going on. The equation on the right is the first one that I'm going to attack. So let's get that one first. It doesn't say about an interval, so we are talking about solutions over the general solution, so plus 2 pi n and all that sort of stuff. So solve that one. If cos x is equal to 0, what are the values of x that solve this? Well, you're going to need that unit circle. Let me zoom out a little bit. Okay, so cosine x equal to 0, that means we are at pi over 2 or 3 pi over 2, right? So x is pi over 2 or x is 3 pi over 2, a little bit of live theater here, plus 2 pi n plus 2 pi n, right? Okay, let's leave it like that for now. Those are some solutions that we have, and then we'll go over here, and I'm going to pause and see if you can remember how to do this one, where you have this 4x. Okay, so we're not going to need to split that up. We don't need to get into double angle and all that sort of thing. Solve that in the style that we saw in 5.3, where you maybe do a substitution. Maybe you put a letter in there, or maybe you can understand how to get there. First of all, divide by, I might as well give you this one. It turns into sine 4x equals 0, of course, because we have 0 on this side. You can divide both sides by 2, and you still have 0 on that side. And now is time for the inverse trig. So maybe you either need to make a substitution with a different letter, and then put the 4x back in there, and work with 2 pi n, or maybe you don't need to. Okay, I'm going to pause and just set that up just to optimize screencast time. Okay, so I didn't throw another letter in there. I just did the inverse sign on both sides. So 4x, we're looking for when is that? So maybe you did a different letter like a w. Sine of w equals 0. Well, the rotation that makes 0 for sine is at 0 rotation, right? Because the y coordinate is 0 on the unit circle there. And then plus 2 pi n, because it happens, it actually also happens at pi, and I'm going to get to that one in a second, but I'm just going to go with this one for now, 0 and every 2 pi after that. So just ignoring the pi for a second, that's the next one that I'll do. So in this case, though, this gets to 0 plus pi over 2n, and actually what's going on here is that this is spelling out the same solutions that you had over there. So when we wrap things up, we've actually haven't found any new solutions technically here, because this one on the right was pi over 2, and then a rotation after that, and then this was 3 pi over 2. And now actually I misspoke there. This one actually is finding more solutions for us actually. So it's going to be this one we're going to keep, because that's happening every pi over 2. So that's actually going to happen if I zoom in at the unit circle. That's going to happen at pi over 2 rotation, and that's going to happen again at the pi rotation. It's going to happen again at the 3 pi over 2. It's going to happen again. So every pi over 2, this guy over here, for every integer, and going in the negative direction as well. So actually, it's these ones that we found first. It's not that they're extraneous, it's that they're redundant. So I'm not going to put a blue box around those. This guy right here, 0 plus pi over 2n, is going to be good. And then, as I said there before, we also could solve where 4x, or 4x equals pi plus 2 pi n. And because what happened there? Because I inverse sine ratio, that's where this 0 came from, and that's where this pi came from. Right? Because that's an angle where the sine ratio is 0. That was our original equation up here. So really my solution arrows point to here and to here. Sort of a double branch off of the left-hand branch. And then, again, we have to divide here by 4. So 2 pi n over 4 means that this is pi over 4 plus pi over 2n. So these are even more new solutions. Actually, this is. So we have to put a blue box around that to emphasize that's part of our solution. Okay, because that's happening now at the rotation just a quarter turn. Pardon me, that's not a quarter turn. That's a, yes it is. Yeah, no, it's an eighth of a turn to there, pi over 4, and then there are some redundant solutions in there, but we'll keep it as is. Okay, so lots going on in that question as an application of product to sum, sum to product. formulas. Okay, there are a couple more examples that have come by way of Mr. Gerst's videos. I'll just show that here, wrapping up mine. There is a verify the identity question. I have the full solution on the Jamboard. I'm not going to talk through that solution. You can take a look at it, and Mr. Gerst has explained that in his video, which is linked to our study guide. And then there's a couple other ones here that don't have solutions here on this Jamboard, but again, he's gone through them in his video for your review. A whole bunch of topics on those three. Okay, thanks very much.